So thanks very much, Rod, for going through the details of that work. That was saves me a lot of time. I haven't included much information on that work, but you may have also cunningly noticed that I've removed the term spatial variability from my title for a number of reasons. One, Michel said everyone else or other people are going to cover it. Two, with regards to time constraints, and three, because it's really pretty hard and I didn't want to deal with it. But obviously, up front as well, obviously going to note my big boss, Phil Robertson, who's been in this business for many more years than myself, and he's helped compile some of these slides. And again, with regards to interaction, please feel free to ask questions, and I would also open up, if I cannot deal with the question, which is possible, others in the audience can chime in who have more experience in certain areas here. So again, I'm just going to be talking about manual chambers, but others in the room obviously have had experience with automated chambers here. And with regards to temporal variability, there's obviously a better coverage of temporal variability with automated chambers, more continuous or near continuous measurements. And we can talk more about that as well. But for the moment, I'll concentrate on manual chambers with the knowledge that automated systems are becoming more common and prevalent, and there are definitely people here, including Peter Grace, who would be willing to chat about the automated systems and how they can overcome some of these temporal issues. So just an overview of the presentation. I talk a little bit about experimental design up front, some theory there, and the ability of choosing the right experimental design with the aim to improve the potential for identifying treatment effects. I'll then talk a little bit about the scales and patterns of temporal variability, and then also throughout the presentation I'll hopefully provide some guidance with regards to some of the practical details of sampling and accommodating the temporal variability. So with regards to detecting flux differences between treatments, obviously the choice of experimental design can really enhance or indeed weaken the study's ability to be able to detect the differences between treatments. As Rod's and many others in the field have done, there's many studies or a number of studies that address the technical challenges of measuring and analyzing greenhouse gas fluxes in the field. There's a little bit less information on the statistical challenges of how flux differences through time can be looked at and across experimental treatments, and less still, although a few out there have investigated the sampling strategies, experimental design, chamber number, plot number, that maximizes the probability of actually detecting flux differences between treatments. In other words, the statistical power of the experimental design. So some key decisions before we even start sampling from chambers and deploying them in the ground is, well, how many plots per treatment? How many assuming you know the number of treatments, but how many plots do we need per treatment? How many replicates, in other words? Should these plots be blocked, randomized complete block or other? If the plots are blocked, how should the boundaries be delineated? How many chambers do we need within each plot? How many samples per chamber to calculate the flux rate? And Rob's alluded to that 4 is a good number, but many others have used 3 or 5 or more. And again, the statistical power can be greatly affected by these and other decisions that are made prior to even putting a chamber in the ground or even constructing one. This is just some work that's in review at the moment from Phil Robertson and Sasha Kravchenko at MSU. I'm not privy to the huge amount of the details of their statistical analysis, but I'm going to present some of the information here that I've gleaned from the draft reviews based on a number of 3 experimental sites in Michigan which have, this is actual data they've looked at with randomized complete block design experiments, 6 replications, which is quite a lot of replications as you can imagine, and with manual sampling of every 2 out of 3 weeks. And they've analyzed this using a restricted maximum likelihood approach. And what you see here, this graph on the bottom, is the total variance in the N2 flux rates attributed to different variability sources. The y-axis is the percent of total variance. The 1 and the 2 represent 1 chamber per plot and 2 chambers per plot within a treatment. And you can see that this residual variance here at the bottom predominates with 1 chamber per plot and pretty much predominates with 2 chambers per plot. Obviously, there's an issue there. The chamber itself is a source of a great deal of source of variance, such that the total variability of the fluxes that we've looked at in these situations is dominated by the small-scale spatio-temporal variations at less than a meter squared, and measurement error sources, so the chamber measurements errors associated with chamber sampling and analysis. So this is really where the error associated with flux measurements comes in, the small-scale spatio-temporal measurements. Here's some more sort of theoretical approaches to looking at optimizing plot number and chamber number, again, before we even start to sample. You can see on the top left-hand table there, we've assumed we were using 18 chambers. We have access to 18 chambers for a treatment, which may or may not be the case. But we look at the statistical power if we're using those 18 chambers, if we put one chamber in 18 plots and 18 replicates, all the way down to using 6 chambers and 3 replicates. And you can see the statistical power decreases with the number of plot numbers as opposed to the number of chambers per plot. Up at near 90, where you have 18 replicates in one chamber, and down to 25, where you have 3 replicate plots and 6 chambers per plot. So in short, I must note that's for CO2 this theoretical analysis was done, but a similar analysis on N2 would yield similar results. The next stage there is to look at the number of chambers per plot for comparing N2 flux differences. Again, between 2 hypothetical treatments, you can see then again on the bottom right graph that the statistical power increases with the increasing number of chambers per plot, such that 1 chamber per plot has a relatively low statistical power to detect differences between treatments, all the way up to 5 and 6, where you may get a much higher ability to predict these differences between treatments. And again, this is theoretical data, and the information's, the nitty-gritty, the weeds are in this review draft, which I'm happy to show people and talk about some of the approaches that they use to get at these graphs. At the moment, I'll pass on the details, rather to make the point that the suggestions, if you want to increase statistical power to evaluate the difference between treatments, the idea would be that you would increase the number of replicate plots per treatment rather than increase the number of chambers per plot, up until a point where the number of replicate plots becomes maximizing because of other logistics. Then ideally you should start to increase your number of chambers per plot. Rod talked more about this again, maximizing the number of gas samples per chamber that you can take in a particular period of time. And also, which is not typically done, certainly myself, I haven't really conducted a lot of this, consider repeated measures analysis of individual chambers. It helps solve a lot of these autocorrelation issues. And by that I mean measurements from the same chamber are typically more similar to one another than measurements from other chambers, even just a small distance apart. And the measurements closer in time are more similar to one another than measurements that are taken further apart from the same chamber. So there's a lot of autocorrelation issues which are not typically handled in papers that we see. But you should take account of it. But in short, consult a statistician. I'm not one. Employ them, make them happy. It really is very useful up front before you even start talking about taking vials out to the field. So now let's talk a little bit about temporal scales and patterns. What are the temporal scales and patterns that we're interested in here, agricultural cropping systems? Probably all, but for the most part, I've just listed the 3 there. Sub-daily, are there diurnal cycles within the 24-hour period? What's the variation across a growing season? What's the variation across a multi-year rotation, a corn, soybean, wheat rotation, for instance? So obviously we need appropriate sampling times and data in order to interpolate these these measurements that are taken, for instance, maybe once every few days or few weeks, and we need knowledge of the temporal emission patterns at the varying scales for the system that we're interested in sampling from. So can we characterize these patterns? I think we can in general, and this is just sort of a 3, if you like, simple pattern types that are out there. This is from originally from Brummer et al., I believe, which is German forest systems, and it was then redrawn in a Canadian study by Pennick in 2006. But basically, just what I want to highlight here is the 3 major types that we can really look at. The top one, before I go on, if you look at the scales here, the actual units of N2O emissions is not important, but actually the scales on the Y scale are important. The top one is 0 to 10, the middle one is 0 to 50, the bottom one is 0 to 200. So you can see on the top emission pattern type, it's really just a background emission type, really low general emissions, no real observable pattern, mostly random. You can't really associate the emissions there with any environmental variable or soil temperature, etc., or even a pulse event due to management. The middle one there, a seasonal emission type, if you like, where you get, over the course of a year, some gradual increases and decreases that are associated with environmental variables, temperature, soil moisture, etc. And then the bottom one there, which may be most common in agricultural systems, but not necessarily, is this event kind of and seasonal emission type, where you have some gradual trends of emission, but also some real pulse events of N2O brought about by management, brought about by natural cycles, maybe freeze thaw, fertilizer, etc. So again, just to summarize, background, low overall emissions, no real obvious link to climate or other controls, and the emission patterns seem to be essentially random. The seasonal system, variable low-medium emissions, gradual increases and decreases, and you can link those emission trends to environmental conditions. And the event plus seasonal, a seasonal pattern which is typically interrupted by intervention, discrete pulses of N2O due to management, or natural cycling, freeze-thaw for example. So here's some suggestions for temporal patterns and how to accommodate them. First of all, know your question. This could be a bullet point right up at the front. Are you testing the differences among experimental treatments, or are you attempting to construct some sort of annual budget for greenhouse gas accounting over 1 year or many years? Know your system. Which pattern operates at your location? What's your best guess as to how the emission patterns will occur over weeks and months and years? And if you don't have a lot of information on the systems, or you can't really identify it through the literature or other sources, maybe it's wise at least to start off with assuming an event plus seasonal type pattern. And in agriculture, that would be a reasonably good assumption. Because if you include or exclude major flux events due to fertilizer, due to rainfall, due to whatever, management intervention, tillage, if you miss these pulses that occur, maybe only once or twice or a few times per year, then obviously when you try to interpolate your data from daily emissions, you're really going to either underestimate or overestimate the total annual emissions. So ideally, what you try to do with caveats is try to couple some background sampling events, maybe one every 2 weeks, once every 3 weeks, in periods of time where you're thinking that the emissions will not be high. So it's not a guesswork, but there's definitely some intuition there. But also then do some much more intensive temporal frequency samplings at periods of time where you think that the emissions are likely to be higher, such as when you apply a large amount of fertilizer to a corn crop. Look at the emissions every day for a few days after that intervention. That would be a wise choice of a strategy. Just some real data from an organic transition grant in corn, soybean, wheat up in Michigan State. And on the x-axis there, you see just the time intervals in months from April 2012 to August 2014. On the y-axis, you see this actually a log scale of N2O flux, so we see some exceptionally high fluxes. But the point of this graph is to show that in this corn, soybean, wheat rotation, CSW, which we started at each phase of the rotation, you see that typically around about early to mid-June, there's a large pulse of N2O flux, huge pulses in the years 2013, 2014. And we deliberately sampled it more times around the events, which was in fact the application of N fertilizer or pelletized poultry manure. So based on experience and knowledge of our systems, we were able to sort of, deploy the chambers more frequently at that time where we made the assumption, which turned out to be true, that there'd be higher emissions. And then periods of time where, for instance, there are limited or less sampling days, those in the shoulder season and the winter seasons, where we typically see less pulses. There are some occasional freeze-thaw pulses of N2O, but we don't really see them much in our system. We don't tend to apply fertilizer. So we can kind of hold off a little bit on the sampling days during the fall and the winter periods, because we know with automated chamber systems that we're not really getting a lot of emissions during that period of time. It saves resources, time, and people don't want to go out in the snow to measure from manual chambers. So just some general information on flux interpolation. Many might know this, but again, talk was kind of geared towards the early practitioners or people who really haven't thought a great deal about doing N2O emissions but really want to get into it. The most common method we have for interpolating data that's taken on a daily time scale to interpolate that up to a larger time scale, a growing season or a year, is just simple linear interpolation, the trapezoidal rule. It's the simplest, it's the most common in the literature, it's very reproducible across different treatments and different studies. And it assumes the observations are good estimates of the average daily flux, which that may not be the case, and we'll talk a little bit more about that, if there's a pronounced diurnal pattern, for an example. There's another general types of approach to interpolation, is the estimation of the duration and magnitude of emissions on unsampled days. So you may look at between correlations between fluxes on sampling days between things like soil water and soil temperature, and use some equations to link the two when you haven't got a sampling day measurement. And that's kind of, you can imagine, some sort of intermediary between simple linear interpolation and more complex modeling. But in general, if there's a lack of information on the duration and magnitude of event-based emissions and the diurnal pattern during the sub-daily emissions, then it's kind of be a really major limitation to temporal interpolation. So it's not a guesswork here. You should know your system well enough so that you can really assign days in which you go out and sample. And you have to be almost proactive and ready to go when, for instance, a rainfall event occurs after a period of a dry spell. It's a case of being quite, having a good team of people behind you, good technicians, or yourself who goes out there and are quite responsive to the environmental conditions and the management conditions that the system has. So just some information or just some literature validation, if it were needed, that manual chambers are great for long-term emissions. Again, we can talk more about automated systems with higher temporal frequency, but this is some 3 examples that I was managed to glean from the literature where they compared various methods, including manual systems, to other more high temporal resolution methodologies. The first one being from vegetable crops in Denmark by Christensen 20 years ago or so. Multiple methods, chambers, FTAR, eddy covariance, and they did a 9-day comparison between all those methods, and they found it was really less than 18% variation of the estimates of the cumulative emissions over those 9 days between all those methods, and the chamber methods were very consistent with the other more high temporal frequency measurements. Again, more information from my home country in Scotland in ryegrass. Keith Smith and others in 2001 and earlier studies looked at manual 3 to 7 day sampling periods and compared that with automated systems that they developed where they measured every 8 hours, and they did that between over a 7 to 48 day comparison. And they found that the emissions, when they looked at the cumulative emissions over the various total periods, were about 14% higher from the automated systems, but there was no significant difference between the manual chamber estimates of cumulative emissions and the automated systems. Tim Parkin himself looked at obviously corn soybean rotations in the US Midwest. He didn't do a comparison of manual and automated, but he used an automated system over a period of 230 days to calculate what we call an expected value. By that, I believe he used the 4 measurements per day, averaged them to an average daily emission, and then linearly interpolated them up to 230 days and called that the expected value of cumulative emissions over that time. And then they did a jackknife sort of Monte Carlo analysis, subsampling of all the automated systems, of all the automated NTO Flux data, and found that if you were able to sample every 4 to 8 days, that your total cumulative emissions over the 230-day period would be roughly plus or minus 20% of that expected value if you took all the emissions into account. So pretty good validation, I think, that manual chambers, if used appropriately, can estimate quite well long-term emissions that maybe other more high temporal resolution systems, which are maybe more complex or costly, would be able to do. So a little bit more about diurnal variability, and I've tried to look in literature to find if there is such a thing as diurnal variability in agricultural systems, and came up with the fact that yes, no, maybe, sometimes. It's all over the place. There are definitely papers that talk about diurnal variability. But the importance is that flux values from manual sampling strategies typically assumed to be conservative, depending on what time of the day you sample. If it's in the morning, typically, or early afternoon, they're assumed to be the conservative or at least representative of the average daily flux. But are they? Obviously, it's important for our estimates of longer-term emissions. So again, with regards to thoughts before you actually put a chamber in the ground, you need to know, do diurnal patterns exist? Look at the literature, find out if the system that you're investigating has shown evidence of diurnal patterns before. Would you expect them in your system? Obviously, the knowledge of any diurnal patterns might improve your understanding of the origin of the NTO production under various conditions, and obviously the understanding of these causes of transient fluxes can help aid in identifying mitigation options and also increase the predictive accuracy of models. So diurnal variability and measuring diurnal variability is really important. I went to the literature to find some information on this, and this is a very, well, an old publication now, but really an exceptional publication for being in 1982, where I haven't found any other papers from that time that look at diurnal variability of NTO fluxes. This is Blackman's from Iowa soils. 2 panels there on the left, corn fertilized, and on the right, fallow fertilized, and the top graphs on each are the actual soil temperature. But you can see from the left panels there, site 1 and 2, I've drawn those vertical dotted lines. You can see that they sampled maybe 6, 8, 10 times during the course of a single day using manual chambers. Presumably a technician did it, but maybe not. But then if you do see some sort of peaks there, round about, if you look about 1800 hours, that would be like 7, 8 o'clock. There's some peaks there of N2 on site 1 and 2 on the left panel. And when you look at the right-hand panel, you do see some sort of peaks in site 1, 2, and 3 closer to midnight, which is not particularly convenient if you want to manually sample. But their overall conclusion, there's really no short time during a 24-hour period that is always satisfactory for assessing the amount of N2 evolved during that period. Some more information from the literature again, from Smith et al., Keith Smith over in the UK in 1998. They did similar comparisons and did multiple manual chamber samplings during the course of a day. And there were definitely periods of time where N2O peak flux was associated with soil temperature, or there was a lag period in time, and they sort of suggested, or the data indicated that peak emissions, when they're coincidental with temperature, soil temperature, that the emissions originated in the upper soil. When there's a lag behind the peak temperature of the peak N2 emission, that the emissions are from a greater depth. This is some more recent data we've got from automated systems at our biofuel cropping station at KBS over a 6 or 7 day period in 2012. So 4 different types of crop system. The x-axis is the number of hours from the beginning, so 0 to about 168. And you can see that, not in continuous corn, but certainly in some of the other systems, in the corn, soybean, and the native grass, you are seeing a consistent peak of N2O at a particular time of the day, such that it's suggesting there is some diurnality to the peak flux emissions. Again, some suggestions. Know your system. Determine the fluxes. You really should be at least doing some sampling to determine if there is a diurnal flux in your system. So I would suggest you do it at least 3 times per day from a number of different treatments and at various times of the year where there may or may not be a diurnal pattern. So maybe at times that display a background type of emission, at times that display a seasonal type of emission, and others where there's an event type flux such as post-fertilization. You obviously want to coincide those measurements with ancillary measurements, soil temperature, soil moisture, etc., at varying depths to try to generate relationships that you may be able to use to determine fluxes between times where you don't sample. And again, based on the results you find, really identify the appropriate time period for daily, the one time that you're going to go out and sample during the day that best represents your average, or at least is a conservative estimate of the daily flux. And typically people will go out in the morning between 9 and 12, but that may be that your system, for whatever reason, has a time where 2 o'clock in the afternoon is ideal. So at least know your system so you can talk about it when you try to publish your work. I'll talk a little bit about what not so much that I call spatial variability here, but more the requirement for the chamber placement in a particular treatment based on the type of management that occurs in that treatment. So what we're, again, is trying to do is place chambers in these treatments that capture the potential variability of fluxes within a single treatment due to the management the management practice. And by that, I sort of mean if there's, for instance, fertilizer banding in your treatment, if there's strip tillage in your treatment or a drip irrigation, such that placing one chamber per plot may not capture the sort of the microtopography created by the management. What you really want to try to do is determine the relative area, the percentage associated by the specific topography in your treatment, and then place chambers accordingly, and then calculate your fluxes from that treatment based on a weighted average. And I'll just give us a quick example of where I've used that recently. As in, I was lucky enough to be part of a USDA project down in Puerto Rico, which is still ongoing. So I went down to try to consult on the best way, or the best way to measure N2 fluxes from Plantain. Just have a quick primer on Plantain. Generates a huge amount of biomass very quickly from a relatively small seedling after a month to an 8-meter tree after 9 months. And they use different types of fertilization and irrigation. They apply in the first few months with drip irrigation, then they hand apply between months 5 and 8, and then they full area apply it between months 9 and 12. So it's really somewhat complex way of applying nitrogen during the growing period of the plantain. So I just came up with some simple ideas which may or not stand up to too much scrutiny, so I'll quickly move on the slide. But what I looked to do was, basically because of the constraints of the logistics, the number of chambers, the cost, and manual availability of people to go out and do the measurements, I thought that it was best assigned if we have 3 chambers, if you like, per microsite, where one chamber is placed really close to the plant itself, and very close to where the drip irrigation, where the N is going in, and another chamber is placed in the alleyway, where some of the residue after harvest is placed, and another chamber is placed, again, close to the drip irrigation line, but between the two plants, where occasionally there's N applied directly to the root of the plant. So it's just an attempt to really get at the potential for the differences in N2 emissions within that microsite of that plot. And you can see from that top right-hand kind of schematic, there is obviously a height difference there, where the chamber 1 is placed maybe 30 centimeters, if you like, above chamber 2, which accounts for the emissions from the alleyway when the residue from the plantain is applied. So just some sort of general idea of really trying to accommodate and cover the potential spatial variation within a treatment based on the management that's associated with that treatment. So again, just some logistical considerations, again, based on my experiences and others' experience. There's definitely many trade-offs between an interreliance, if you like, between the total number of chambers to sample from, the time taken to sample from each chamber, how long does it take you to go in and take your vials and get your samples from the headspace, the number of gas samples per closure, 3 or 4, as Rod was talking about, the time interval between the sampling rounds, do you want to sample every 5 minutes, every 10, every 20, how long? The sampling route, the actual geography of the site, how long does it take you to get between chambers? And also, if you want to take ancillary measurements during that time when you're sampling, how long does it take to do that? So just some general recommendations if you're out in the field and trying to work out how long it's going to take you to sample and how long it takes you to get back to the first chamber that you need to sample from again. Do prepare your sample vials, obviously, in the order of the collection in the field. If you've got lids in your system, go out and place them first. Don't wait to place them and carry them around with you. Place all the vials you need in place before you even take the samples. If you're looking at measurements of height and volume, obviously which you should be doing each time you go out and sample to calculate fluxes, go out and do that beforehand, if need be, just prior to the flux measurements. Our experiences in our systems with our approach of sampling, and there's a lot can be talked about how you actually go out and sample from a chamber and insert it into a vial. There's a little bit of information there which we can chat about. Allow about a minute. We find that good technicians, if you like, not including myself, needless to say, can manage one chamber per 40 seconds. They're exceptionally quick and exceptionally good at it. But others may take much longer because they're just learning their trade, if you like. Do allow extra time if you're going around a sampling round when you have to deploy the lids. Obviously, that's going to take a bit of time depending on your mechanism, your chamber design. And again, allow extra time between these measurements if you're going to take ancillary measurements during the time where you're also sampling from a chamber. What our general experience is that if one technician or myself goes out there, we really try to limit the number of chambers we're sampling from, irrespective of the orientation, to about 15 or 20 chambers per sampler per sampling event. Any more it really extends the period of time over which you're taking the 3 or 4 measurements up to an hour and a half or more, and we have other issues associated with long chamber lid deployment, which Rod and others can definitely talk about. But I'll just finish off with some more general suggestions about my experiences and Phil's experience. Choose an experimental design and a sampling strategy up front that helps you maximize the possibility that you're going to detect any flux differences between the treatment, i.e. the statistical power. Improve your statistical power of your experiment before you even think about going out and sampling from a chamber. And most generally, try to sample maybe according to event and seasonal type patterns, unless you're very knowledgeable of the system beforehand or have good ideas of what the emission patterns are going to be, or unless, of course, experimental objectives dictate that you don't need to use that approach. And do conduct sampling to determine the diurnal variability of the system at various times of the year when emission patterns are likely to vary. Account for the management practice within individual treatments by appropriately placing the chamber. And for the most part, don't sacrifice the quality of the sampling strategy for the quantity of the sample. That's another little proviso I'd put on there. Really concentrate on getting your sampling techniques, your chamber placements, your deployment, your lid deployment, your vial placement. Really concentrate on getting the quality of that as high as possible before you worry over necessarily about the number of samples you're taking. That's where a lot of the errors I talked about came from. The actual sampling of chambers, the small-scale measurement errors associated with bad sampling procedures, bad handling procedures. Get those right down before you really start to really worry too much about the number of samples you're taking, even though it's important. And so with that, thank you, and take some questions, and maybe enlist other members of the audience to help me if I struggle with the answers. Thanks very much.
Okay, so if you're only taking 15 to 20 samples per event, you're not going to do very many treatments. I'm wondering if there's a way to maybe sample one rep one day and another rep another day. Have you tried things like that? It's kind of tricky because then you get into how far you are after a rain and all that. So what do you suggest?
Yeah, I mean, we are lucky with our long-term experiments in Southwest Michigan, where we have 5 to 6 technicians each year who are dedicated to gas sampling as well as soil sampling, so that we're able to accommodate. If each of those technicians can handle 15 to 20 chambers, we can do multiple treatments, multiple chambers in a single morning. But you're right, if you don't have an adequate amount of manpower, then you're going to have to play these trade-off games where, for a background emission type, that wouldn't be much of an issue, I would imagine, if you've got a period of time where you kind of know there's going to be the same type of emissions occurring. and sampling on the next day would be fine, I think, based on other logical considerations. But if you've got, as you say, a peak event where you've applied fertilizer on day one, you got to play the game of where should I best focus my resources. What's the treatments that I really want to get emissions from on that next day after that, for instance, that fertilizer application. People can do more than that. I'm just giving you a general guidance. If you want to go around and sample, for instance, every 15 minutes, if you have 15 to 20 chambers and it takes 1 minute per sampling to get the gas out, and you've got other measurements, by the time you get around to your first chamber again to take the T0 or the T1, 15 or 20 minutes have elapsed. If you do that 3 or 4 times, you're talking over an hour of chamber closure, which is the point where things start to get a bit, although there are obviously Rod's work shows you can handle that, but ideally you really want to sort of minimize your chamber deployment time to under an hour. That's a typical suggestion. So you've got to play with all these trade-offs.
Would you say most of the things you said about accuracy would apply to CO2 measurement, and previous speaker would apply to CO2 measurements as well as nitrous oxide?
Well, when we do CO2, we use we do analyze for CO2 from our hourly chamber samplings, but we use it more, as Rod suggested, as a proxy for detecting issues with the N2O. We have Lyco measurements and others, so we don't rely on the 1 hour deployment time to calculate our CO2 fluxes from the system. We have more shorter-term measurements of CO2, which we can use. We do use them from time to time, depending on the system, but what we most likely use them, or what we use them for typically, is detecting issues with the N2O and the methanes based on vial swapping or whatever other sort of common error that occurs during the handling of vials.
What do you suggest about the number of chambers per plot size? In some cases, you can have small plot size, but in some cases, you need to have a big plot size. For example, the yield or yield measurement, or some in the grazing experiment, that's maybe a half an acre size of plots.
Right.
What do you suggest? I mean, there will be so much variability in the soils between the
Right.
plot sizes. How many number of chambers per plot you suggest according to plot size?
How long's a piece of string? What I've seen do in the literature is that ideally what you want to be doing is peppering that 1 acre site with multiple chambers initially, looking at sampling as much as you can, maybe 20 or 30 chambers or more over half an acre, and then looking at what's the least number you can get away with based on the variation associated with that particular chamber and field. I can think of work off the top of my head by Eric Davidson in 2002 in forest systems, where I think they put 36 chambers down and then, analyzed all the flux data from 36 chambers on a number of days, and then worked out using, the deviation of the emissions, what was the least number they could practically get away with, and they came up with a number of like 6 to 8 per field. I'm not saying that's the number you should use, but that's what they kind of came up with based on their original multiple chamber analysis. But a smaller plots, you may not need so many as that, obviously.
I'm not sure if this is going to be covered in another presentation, but can you please comment about the issues or the errors associated with the sampling technique, and what are the factors that we should take into consideration, like the sample volume and things like that?
Wow. Yeah, I haven't done the analysis. The physical going out with your vials, with your syringes, and actually taking samples from. They're typically errors that was mentioned before: vial swapping, bad labeling. Ideally, you obviously, our method is, what we do is we obviously prepare our vials beforehand, but we don't evacuate vials. I can just do a little bit about. We go out into the field with vials from their Exitana vials, and we go out with them, and we pre-flush, for instance, our vials before we put a sample in. So each time we take a sample, we take a proxy sample, if you like, push that through the vial in order to condition the vial to the upcoming sampling event. So you really need to employ good technicians, good people who can learn and who can really be as precise and accurate as they can with each individual vial. Errors are creeping everywhere, but you want to try to minimize them with regards to your methodology for actually collecting the flux. So employ good people, train them well, evaluate how well they're doing, and have, for instance, take CO2 measurements as well to really check if the N2 emissions are the N2 concentrations over time are what you would expect from that system. Others maybe want to chime in with regards to measurement areas from sampling, but that's kind of my first approach, my first take at it anyways.
thanks for the
Hi, Louise.
interesting presentation.
Sure.
You could do a lit review now.
Say again?
Write a lit review. Could put this all together. I think it'd be nice to see it as a lit review.
Definitely.
Can you, and Rod might want to chip in here too, give us some insights into sampling in grazed systems, because of course that's their extra dimension of animals and dung and urine and compaction as a result of treading.
So temporal, I mean, spatial that's people model, but also we've got colleagues, again, because of our luck with the number of technicians we have access to, we have people sometimes that look at cows and see when they poop and pee and go and put a flag where they did that, and then follow up with the sampling very soon afterwards. So we can account for spatial coverage of excrement, if you want to call it that. Temporally, again, the same sort of suggestions I've just given would, for the most part, apply there, but spatially with regards to graze systems, that's obviously a difficult one, and a lot of manpower is needed with manual chambers, but we look at where the cows do their business and follow it up with flags and then measure to get ideas of where the most concentration of N2O potentially could be, to try to have, try to put a boundary on what the total emissions from a deposit of urine or a deposit of excrement would be. And that's how, I don't personally do that. A colleague who does that in the dairy farm, he would definitely have more information on that, and maybe others who've sampled from grazed systems would be happy to add.
One of the ways we've dealt with very large chamber designs and large plots is that rather than having an individual trying to sample all 4 times, we have 4 individuals going through, so there's a time 0 person, a time 15 person.
Right.
And that allows you to do a larger number of samples fairly effectively.
Yeah, we've thought about that, yeah, and that's right, that's a good idea. We have multiple treatments and multiple chambers per treatment, so we employ them each on a per treatment basis, and they do the T0s and T1s all by themselves. But again, that's a perfectly legitimate approach to do that. Oh, okay. Sorry, I missed that. How do we calculate the flux? Oh, which approach, linear, quadratic? Well, for the most part, we've defaulted to linear in the past, but we've recently developed a kind of modified HMR approach, Hutchinson-Mosier, Pedersen, our approach, and we've chatted with Rod about the best way to approach our flux measurements. So now we're typically doing, we have a methodology which kind of defaults to linear, but when certain conditions are met, we then use an HMR method. Yeah, so linear HMR, in short. Hi, sorry.
When you start your experiment in your time 0, when you put your chamber, it takes like 10 to 15 or maybe 20 seconds. And it's different from person to person. And when you come back in your time 1, you don't have that lag of 10 to 15 seconds. How do you quantify that in your statistics?
So you're talking about the time it takes to put a lid on
and then I start sampling.
and then sample from.
And you don't have that in your time 1.
Well, we've looked at using ambient air at the site as another means of calling that T0, if you like, as well as the T0s that we take after the lid has been put down. And we found there's not a lot of, no real difference. We've if you like, replaced the real T0s when the chamber lid's down with the ambient T0s from the site on that day in that area of space. And we found there's no difference. So we do typically use the T0s that are sampled 15 or 20 seconds after the lid is placed, but there's no difference between that and ambient for the most part, in our experience. Hey, Rod.
Hey, yeah, so we do the same thing on that. We sample from right above the soil before we put the chamber down, and that's when we start the clock ticking, so to speak. Yeah, so you covered a lot of stuff, so very nice job. Just one point a caveat I wanted to make about fertilizer application and the dynamics that happens after that. You can see that peak occurring anywhere from a day to 3 or 4 weeks. So it's difficult to kind of guess that. So if you're going to adjust your sampling frequency, it's tricky and it's risky to do that. even for rainfall events, it's not always clear when that response is going to happen. So,
Yeah.
so saying, it's going to happen a day or two after the fertilizer event is a little bit risky. I've seen it happen 3 or 4 weeks. Depends on soil temperature. It depends on how quickly that nitrification kicks in and things like that. So we kind of used that Parkin paper in the way that he did it was blind to that. So when he selected his sampling frequencies, it was just 3 times a week or 2 times a week or every 3 days, every 4 days. And so we just stick to that,
Right.
regardless of what else is happening.
Yeah, and,
So-
in our longer term, bigger experiments, we do the same. We're sampling every week or 2 weeks and not looking for event pulses. And you're, of course, right that we've seen that delayed pulse based on rainfall events and soil moisture 2, 3 or more weeks later as well. This is more general, obviously, guidance that, when you have an event, an intervention event, which you think may cause it, it may be wise to sample a day or 2 afterwards and then go back to your GC and look at the fluxes, and if nothing's happening, then kind of hold off for another. Peter will talk more, maybe Peter goes about automated systems. Obviously, that kind of helps solve the problem there. So ideally, what you're really trying to look at is if you have the resources, is a manual chambers and backing it up with some auto chamber measurements as well to try to, as I've talked about with that literature, it's not an easy thing to guess N2O. In fact, don't try to guess N2O, bad idea. But have some idea of your system, have some knowledge of when events which cause pulses, and try your best to capture them with the resources that you have. Sure.
Okay, I guess my question might have already been partially asked or addressed. My question is, when you're doing these manual samplings, I guess people don't usually go out sample when it's raining. And for
not often. Yeah. Anyway, sorry.
yeah, and I guess if for some regions it may be raining, I don't know, 60 days a year, and so how do you account for that?
Well, I mean, luckily in the Midwest, we don't have that issue. We have 60 years of drought in 2012, 60 days of drought. But again, people, unless the site is compromised and you're up to your knees in mud, where you're going to have, issues of foot traffic around chambers. If it's raining or drizzle or whatever you want to go, we still go out. It's not necessarily a problem. But you're right. But again, know your system. If you know that rainy season comes 60 days in March and April and May, then go out and sample appropriately during that period of time so as to get your best estimate of the emissions during that period of time. Just general guidance. You got to play it by ear to some extent.
Oh, hello. Yeah, thank
Hi,
you.
sorry.
That's me. Sorry. And I'm very glad in your talk you covered how many numbers of chambers you should put in the field, and for each treatment, and because it's such a laborsome work to do the chamber flux measurement in the field. We had the experience because sometimes I'm limited. I had only 1 technician, and sometimes I have 2 technicians. Right. You really cannot do too much. Right. I agree with that. We focus on much more on the quality of the data, make sure the method we use, the procedure consistent to get the flux values, because we don't have the ability to put more chambers on it. So with that limitation, what we do is I think we should also consider the time replicates. Is that we did 1 year, we did not have enough replicates, and next year, since we can replicate the same treatment in the same field, and we do another year, and the treatment effect, they agree each other. So just a comment, I think.
Yeah, no, absolutely. All right.
Thank you. This is wonderful conversation. We are going to move on to our next speaker to stay on time. Thank you.
Thanks.